Sodium, a very unstable metal, doesn't exist in the natural state, reacts violently with water. Chlorine, a heavy greenish-yellow gas, so poisonous that it was used as a weapon in the First World War. Two very reactive elements. But if you burn sodium in chlorine, you get salt. Ordinary everyday table salt, well, almost. It makes our food taste better, but more importantly, it's an essential ingredient in most healthy diets. In nature, most salt is to be found in the oceans, and for thousands of years man obtained the salt he needed by evaporating seawater. He used it to preserve his food, treat animal skins to make leather, and even as a currency. Its chemical properties, and the relative ease with which it dissolves in water, were to play an important part in the industrial and technological revolutions that transformed Britain throughout the 18th and 19th centuries.
My family have been in the salt-making business since the year 1721. But as far as this particular site is concerned, we moved up here in 1842 because we found that there was a brine stream below Marston. We're pumping up the brine, which is formed, incidentally, naturally, about 160 feet below the ground. That's formed by rainwater and river water seeping down, dissolving part of the brown rock salt, and forming this underground brine stream, which is about 8 times the strength of sea water. We pump it up out of the ground using the nodding donkey beam pump and the steam engine, of course. And then it goes straight into a big tank up at the other end of the salt works, where it's stored until it's used and put into each salt pan that we're using. After that, 4 fires are lit underneath the salt pan, and about 6 to 8 hours later the brine is boiling, or as we say in the trade, chuckling. A white scum eventually appears on the surface of the brine. That quickly forms into little salt crystals, and as the salt crystals gather in weight and size, they then sink to the bottom of the pan.
Though largely displaced by modern vacuum evaporation, this technology lingers here in a form that would have been familiar to the Romans. Although its use in this part of Cheshire was not recorded until the Normans meticulously itemized the productive wealth of Britain in the 11th century, the Domesday Book lists saltworks around the towns of Middlewich, Northwich, and Nantwich. In the mid-1700s, it was realized that salt could be converted into the alkali needed by the booming soap and glass industries. This was the beginning of the great salt-based Cheshire chemical industry. But as these industries grew, so did the rate of natural brine extraction, sometimes with dramatic consequences. Subsidence was inevitable. As groundwaters were pumped up from the bedded salt below, so it was replaced by fresh streams that circulated over the layers of rock salt, dissolving more and more until the surface collapsed. Throughout the 1800s and well into the 1920s and 30s, scenes like this were commonplace in the salt-producing towns of Cheshire. To deal with the problem, the people of the area developed a technique using timber frames that allowed them to jack up their buildings and so restore levels. The house on the left had been built in the ordinary way, and so, as the pavements and buildings around it were raised, it was left behind, eventually to be abandoned. Today, the problem has been all but solved. but the town's pleasing Tudor appearance remains, a monument to its people's determination to stay, and to stay upright. What is it about the chemistry of sodium chloride that has made it so valuable to man that he's put up with so much inconvenience and strives with such ingenuity to extract so much salt, and to cope with the consequences? Well, we can start to find an answer by looking at the structures of the atoms of sodium and chlorine. All atoms consist of a nucleus made up of protons and neutrons, so it carries a positive charge. This nucleus is surrounded by electrons with a balancing negative charge. Now, the electrons are not just randomly arranged around the nucleus, but lie in well-defined regions corresponding to specific energy states. These are the orbitals or energy levels. Now, some elements are known to be chemically inert or very unreactive. These are the inert gases, sometimes called the noble gases. For example, helium, neon, and argon. When we look at the outer electron structure of these inert gases, we find that they're all the same. They all contain a filled S shell and a filled P shell as their highest energy levels. That is, the outermost levels contain 8 electrons. It's thought that the very unreactive nature of these elements is due to this type of electronic structure, and that when chemical reactions occur with other elements, it's because they're trying to acquire inert gas types of structures. So let's look at sodium. This has a structure almost identical to that of the inert gas neon, except that it has a single extra electron. If sodium could, in some way, lose this electron, it should become much more stable. But what about chlorine? This element has a structure almost identical with the inert gas argon. The only difference is that it's short of 1 electron. Therefore, if it could gain an electron, we might expect it to become much more stable. Not surprisingly, when sodium and chlorine are put together, they readily react, with sodium atoms giving up an electron to the chlorine atoms. They both become more stable, but the net result is that some of the positive charge on the sodium nucleus is no longer balanced by the surrounding electrons, and so it appears to carry a net positive charge. Similarly, the chlorine atom now contains 1 electron more than is needed to balance the charge on the nucleus, and so exhibits a net negative charge. As a result, we talk about positive ions of sodium and negative ions of chlorine. But charges of opposite sign attract each other, so sodium ions and chlorine ions will readily stick together to form a solid, held together by strong electrostatic forces. They don't form molecules in the sense that 1 sodium atom is bonded to 1 chlorine atom, but rather they form an ionic lattice, in which each sodium ion is ionically bonded to its 6 nearest neighbor chloride ions. Similarly, each chloride ion is ionically bonded to 6 neighboring sodium ions. But what about water, the other component needed to form solutions? It too has some very interesting electrical properties. The rod is holding a strong positive charge. As the water comes close to the rod, the molecules orient themselves so that their negative ends point towards the positively charged rod. Since the negative ends of the dipoles are now nearer to the charged rod than the positive ends, the attraction of the negative ends is greater than the repulsion of the positive ends. So the water is attracted to the rod, and the stream of water moves closer to the rod. The fact that water molecules are relatively small, so that they can approach other ionic and molecular structures closely, and the fact that they behave as dipoles are the main reasons why water is usually a very good solvent for ionic salts. So how does water dissolve an ionic salt? When sodium chloride is dropped into water, the water molecules cluster around the ions on the surface. The negative ends of the water molecules preferentially attach to the positive sodium ions. and the positive ends of the water molecules preferentially attach to the negative chloride ions. In this way, the strong ionic bonds are weakened until the ions eventually break away from the surface of the solid, exposing further ions for the process to repeat itself. We usually summarize this process by the dissociation reaction, written as the equation NaCl solid goes to Na plus aqueous plus Cl minus aqueous. Water's powerful solvent ability still forms the basis of modern salt extraction techniques, and today salt is an important raw material in the chlorine and alkali chemical industries.
In this area of Cheshire, there are very large deposits of salt underneath the Earth's surface. They were deposited some 220 million years ago during the Triassic period, and they form very large layers or beds. The topmost point of these beds is some 600 feet below the Earth's surface, and the salt itself is some 600 feet thick. It is an ideal deposit to be worked by a technique known as solution mining. An ICI has been solution mining of salt on this site since the mid-1930s.
From this control room, in the middle of ICI's Holford brine field near Northwich, the working of some 50 to 60 operational wells is constantly monitored. 24 hours a day, their pressures, flows and brine strengths can be checked, recorded and adjusted. From the surface, there's little to see. But the occasional outcrop of curiously shaped tubes and valves tells us that this is no ordinary field. Underneath the surface are boreholes that go deep into the rock salt below. And all around, just below the depth of a farmer's plough, is a network of pipes that carry millions of gallons of water with their valuable cargo of sodium and chloride ions.
The technique involves the creation of a series of isolated cavities. The first stage in this is that we drill a borehole approximately 17 inches in diameter to the bottom of the salt, and then set inside this borehole 3 concentric sets of steel tubing. In the outer annulus, we place high-pressure air, and we pump high-pressure water down the next or inner annulus. This dissolves some of the salt and forms a solution of approximately 25% of sodium chloride in water, and that brine, as is known, comes back to the surface under the pressure of the water.
Though the technique may sound simple, it's important that the brine being brought up to the surface comes as close to saturation as possible. Weak brine contains fewer ions, and the successful commercial operation of these fields depends on the most economical extraction of the salt below. So daily, manual checks are still carried out, despite the impressive monitoring that can be made from the control room. "42 degrees on the hydrometer tells the operator that his well is working close to the optimum. But what is it that limits the amount of salt that a given volume of water can dissociate? What is a saturated solution? A crystal of salt is dropped into water. Sodium and chloride ions on the surface are detached and go into solution. This process continues. But after a while, we see that the number of ions in the solution becomes so great that the chance of ions rejoining the surface increases. Eventually the state is reached where the number of ions leaving the surface of the crystal is exactly the same as the number returning to the surface. When this condition is reached, the number of ions in the solution remains constant. In other words, the solution has become saturated. So when we think about salt dissolving in water, we have to think about 2 reactions occurring simultaneously. There's the straightforward dissociation reaction we've already met. NaCl solid goes to Na plus aqueous plus Cl minus aqueous. Then there's the reverse reaction. Na plus aqueous plus Cl minus aqueous goes to NaCl solid. In other words, we've reached a state of equilibrium. But there's more to it than that. At equilibrium, the forward reaction and the reverse reaction both continue, so that although the number of ions in solution doesn't change with time, there's a continuous interchange of ions between the solution and the solid. This is called dynamic equilibrium. Now, it's not difficult to show that saturation is indeed due to a dynamic form of equilibrium. This is a saturated solution of sodium chloride. The white crystals in the bottom are crystals of salt, and we've left it standing like that for a while just to make sure that the solution is saturated. Such a solution is non-radioactive, and we can test this with a Geiger counter. The counts that you can hear are simply due to background radiation. This is a sample of radioactive sodium chloride. Chemically, it's identical to the ordinary salt. The only difference is it's been made using a radioactive isotope of sodium. We can soon show that it's radioactive. What I'm going to do is add the salt to the solution, stir it, and filter it. If the equilibrium was static, then the final solution should still be non-radioactive. On the other hand, if the equilibrium were dynamic, then some of the radioactive ions will have gone into solution, some of the non-radioactive ions will have come out of solution, and the solution will be radioactive. Well, let's see. Bring the counter up. Final solution is radioactive, therefore the equilibrium must have been dynamic. But how can we describe the amount of salt that will dissolve in a given amount of water to produce a saturated solution? The simplest thing would, of course, be to take a known volume of solution and evaporate it to dryness. Then weigh the mass of salt left. For salts that readily dissolve in water, solubility is usually expressed in this way. But this doesn't tell us everything. Look at this. If we add a strong solution of hydrochloric acid to a saturated solution of sodium chloride, white crystals separate out of the solution. These are, in fact, pure sodium chloride crystals, which slowly settle to the bottom of the jar. You might have thought that by adding the acid, and so increasing the volume of the solution, more sodium chloride would have gone into solution. In fact, it has precipitated some out. Why? It's pretty clear that the amount of salt that dissolves in water doesn't depend only on the volume of water. It also depends on what else is present in the water. Here, hydrogen ions and chloride ions from the hydrochloric acid. So what we want is some way of describing a solution in terms of the number of ions present in the solution. If we consider the concentration of ions in solution, that is, the mass of ions per unit volume, then we find that for sodium chloride, the product of the concentrations of sodium ions and chloride ions in a saturated solution at a specified temperature is a constant. We can write this as KSP equals Na plus times Cl minus, where the square brackets denote concentrations, and the constant KSP is called the solubility product. For sodium chloride, the solubility product is about 40 moles per litre all squared. Now suppose we try to dissolve sodium chloride in water that already contains chloride ions. Suppose that X moles per litre of salt dissolves in water already containing 1 mole per litre of chloride ions. The concentration of sodium ions will be X moles per litre, but the concentration of chloride ions will be 1 plus X, moles per litre. So the solubility product will be x times 1 plus x, and this must be equal to 40. Solve this equation, and you'll find that x is about half the amount of salt that would have dissolved if there'd been no chloride ions already dissolved. So it's not after all surprising that if we add hydrochloric acid to an already saturated solution of sodium chloride, some of the sodium chloride will separate out of the solution. Here then is a way to describe the behavior of solutions that takes into account the effect of any other ions in solution. Essentially, we can define a solubility product for any pair of ions, one positive and one negative. And in any solution containing these two ions, the product of their concentrations can never exceed the solubility product. The important thing to notice is that it doesn't matter where the ions came from. All that matters is that they are present in solution. This is a very important point, and one that lies behind many of the processes used by the modern salt-based chemical industries. Water's great solvent ability is not, of course, confined to sodium chloride. Analysis of the brine that ICI extract from their Holford brine fields shows significant amounts of other soluble salts. And here's where solubility product comes in. Mike Neal again.
These calcium and magnesium salts, if not removed, will have an adverse influence on the plants downstream which use the brine as a starting material. And so from Holford, the brine flows down a series of trunk mains by gravity to a brine purification plant at Lostock. The purpose of this plant is to remove soluble calcium and magnesium salts. In the first stage of treatment, we add sodium carbonate in solution, and the additional concentration of carbonate ions causes the precipitation of calcium carbonate, because in fact the ionic product or solubility product of calcium carbonate is exceeded. Shortly after this, we also add caustic soda, sodium hydroxide, and the additional hydroxyl ions that we've added result in a precipitation of magnesium hydroxide together with the calcium carbonate. And the brine then, instead of being clear in appearance, takes on a cloudy white, rather like whitewash look. And the final stage of purification involves the settling of this calcium and magnesium precipitates in a series of vessels known as settlers.
The calcium, now as calcium carbonate, and the magnesium as magnesium hydroxide are collected from the bottom of the settling tanks as a very fine white sludge. The brine, which before purification contained about 2,000 parts per million of calcium and magnesium, gently overflows from the top of the settlers, with the level of these impurities reduced to less than 15 parts per million. From here, it flows into a reservoir ready for use in the manufacture of chlorine and sodium hydroxide, which are then used as the basis for a surprising range of products.
Just a little atom of chlorine, valence minus